Should be fine now. Well, hello. That's an official hello now. And, oops. I guess that's not a good idea. You have to press a number which represents the answer to this question. That's a timer. So my understanding is that many of you want to become doctors, right? So imagine you have a visitor, a guy, overweight, heavy breathing. He tells you the only food he eats is junk food, doesn't exercise. What do you say? If you follow the same path, you may run into troubles with your health. You have to be honest. Well, if you don't know how to answer this question, you may run troubles with your first exam. You still have 7 weeks ahead of you. It's a lot of time. Some people think that God made the whole universe in 7 days, so 7 days is a pretty long time period, right? So if you're still not sure how to do some of the homework problems, you have 7 days. Next Wednesday. What day is today? 14 days, twice more than God had. So you're all set. Don't worry about this question. What happened? Yeah. Time. Time was up. So you're ready? And I want to believe you knew what to answer, you just missed the right button. Well, so let's do it. Of course, it looks like a simple question, but it tests our understanding of the very nature of the Newton's second law. First of all, this symbol represents the net force, which is the sum of all forces. So if you want to calculate the acceleration, that's what we have to do, literally. That's what it literally is happening. Now, of course, we have to step away for the moment and recall how to add vectors. There's a tail to a head rule, which we must apply, again, literally. So the result is this. And of course, if we take a vector and divide by a number, we get another vector. In this situation, it's a shorter one. And if we want to calculate the magnitude of the acceleration, which is this vector, well, magnitude, we have to now place it everywhere, magnitude, magnitude. We need to know the magnitude of this long arrow, which comes from the Pythagorean theorem applied to a right triangle, divided by the mass, which we know. Oh, we have eyes, brain recognized. So a lot of things happening, but the result is 1. No questions. Well, we've seen this slide before, one way or another. And from now on, we just have to learn how to apply this law to solve many problems, to answer many different situations. There are a couple of more equations we will learn, hopefully today. However, from the theoretical point of view, we've covered 97.65% of everything we need to know to solve all homework problems. So, what's happening here? Well, again, remember, in general, this law leads to only 2 different situations. The situation number 1 we call equilibrium. The situation number 2 has no name, just general situation. And the equilibrium happens when the net force equals 0 and the object is at rest. And that's exactly what we see here. The net force is equal to 0. That's the condition we have to apply to answer the questions about, well, forces. Of course, we need to redraw the diagram. We don't care if it's a poor lady on the rope or a light on a cable or a monkey walking the cable. Doesn't matter. There is an object and the force of gravity is acting on it. The magnitude of this force equals 60 kilograms times g, which is about 600 newtons. And we also have 2 other forces. We call them the force of tension and this angle equals 10 degrees. This angle equals 15 degrees. And that's it. Now we just have to apply the condition for the equilibrium. We can do it differently. So first we can write that the sum of all x components must be equal to 0, as well as the sum of all y components must be equal to 0. This vectorial equation, in fact, is an equivalent of 2 algebraical equations. We cannot use these equations yet. We have to choose x and y axis first. And the natural choice always pointing one axis parallel to one of the forces and another axis perpendicular to the first axis. That's it. It doesn't have to be now horizontal and vertical. When we talk about forces, we choose the axis to make at least some of these components to be equal to 0. So in that case, if we choose at least one axis parallel to at least one force, at least one component will be equal to 0. So we can choose for example, what letter do you like? It doesn't have to be x and y. Why not? P axis pointing down, and I need one more letter. Why not? P and Q. There's actually kind of standard pairs in physics, X and Y, T and R, P and Q, V and W. I don't know why. Nobody knows. It just happened. So in this situation, of course, if we choose P and Q variables as our axis, we have to rewrite our equations P, 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 Q, Q, Q. Now, this green letter represents the Q component of the tension number 2. This green arrow represents the Q component of the tension number 1. And the Q component of Mg so Mg is also what we call a weight. So the Q component of this force, weight, is equal to somebody has to say something. Number 0. So why not so sure? Okay. My stream died. 0. So this simplifies the second equation. Yeah. Tension number 1 has a positive component relative to the Q axis. So T1 times, and the green arrow is the opposite to 15 degrees, sine 15, plus. The tension number 2 has a negative component relative to the Q axis, right? So negative component, which will be equal to the magnitude of that force times what? Well, the green arrow, which points to the right, is adjacent to 10 degrees angle. So cosine of 10 degrees plus the Q component of weight is 0, and that equals 0. This is the first relationship we can write using the Newton's second law for equilibrium. And this is an equation which has 2 unknowns. We can apply the Newton's law to the first equation, write it down. That gives a second equation with the same unknowns. 2 equations, 2 unknowns. It's solvable. Mathematics is up to you. Yeah, that's a physics class, not math. There is another way which I personally prefer. So this is what I would do, because that, from my point of view, saves time. So we have force of gravity, 600 newtons pointing down. If we need to add 2 forces, we have to add tension number 2, like this, and we have to add tension number 1, like that. And the result must be equal to 0. So we have to end up at the same point where we started. And we know this is 10 degrees, and we know that is 15 degrees. The picture, remember? T2 at 10 and T1 at 15. And this is a triangle. If you draw a perpendicular like this solution will be the mathematical equivalent of doing what we've done just a slide before. This is the statement about this side. You see, this triangle and this triangle, they share the same side. So if you want to use this triangle, you're calculating this side, you have to get exactly the same result as you've been using this triangle and calculating this same side. This is basically exactly same kind of reasoning if you had chosen this axis and writing the components relative to this axis. But another way is applying the sign theorem. For example, again, this long arrow represents the force of gravity, 600 newtons. So this arrow represents the magnitude of this segment, not arrow anymore, represents the magnitude of the tension number 1. This angle is equal to 90 minus 10, 80 degrees. This angle will be equal to what? 360 minus 15 minus 80. Oh, 180, 360, that's the whole thing. 180 minus 80, 100 minus 15. What? Yes, that's exactly what I thought. So T1 divided by sine of 80 is supposed to be equal to 600 divided by sine of 85. You can immediately calculate the magnitude of this force. Well, moving on. We had an example of a problem involving two objects. This is another example of a similar situation. What do? Well, first we have to write as many Newton's laws as we can. Normally, we can write more than we need. But how would we know until we try? So how many Newton's law can we write? Well, first of all, this big green box represents a system made of a single object, so we can write the Newton's law for this object. This smaller blue box also represents a system. We can write the Newton's law for this box. But that's what we see when we look at it. The nature doesn't care what we see. From the point of view of the nature, this whole combination of two boxes also can be treated as one whole system. We can imagine that we nail them together or glue them up. So we can write 3 Newton's laws. We can write the Newton law for individual part of a system, and we can write the Newton's law for the whole. So let's do that. For the green, well, first free-body diagram. There is a force which equals 15 newtons and points to the right. Now, how many more forces should I add to this diagram? This is an actual experiment. We should neglect friction, but we cannot neglect gravity, and we cannot neglect that force which supports it from the bench, which we call normal force. So, my question to everyone, prepare your clickers, please. Done. No more forces. We have more forces acting on this green box. What? There is a sign-in sheet somewhere around, if you're asking. If not, I don't know what you're asking. Or you should be louder. You see the timer is running, so someone else might have a different setting, because if you've pressed a number, any number from 0 to 9, that would be counted as a response. The feedback means something weird had happened. The channel is 21, and all right. This is about a definition of force. A force is a measure of interaction between two objects. There is no such thing as self-action. It doesn't exist in nature. So if we have two objects touching each other, it has to be some kind of a force. And we do have two objects here touching each other. The green box is touching the blue one, and the blue box is touching the green one, and go away. It must be one more force acting between these two boxes. So there is a force acting from the green on the blue, but that cannot be a part of this free body diagram. The part of this free body diagram is supposed to be the force acting on the green from the blue. One more. So 4 forces. And gravity and normal cancel each other out. So the acceleration points to the right. If we push to the right, it travels to the right faster and faster. So the natural choice for the axis is to the right. Relative to this axis, the Newton's law looks like this. M, well, green times A green, has to be equal to the applied force points to the right, so it should have a positive component, 15 newtons. The force acting on the green from the blue points to the left, so it should have a negative component. So this is how we can write it, plus some negative number. So 2 vertical bars always represent the magnitude of something. So this expression explicitly shows a negative number. It's -1 times some positive value. But this is what we don't know, and this is what we're looking for. This equation has 2 unknowns. We cannot use it. Well, moving on, there's another object we can write the Newton's law for. The blue box. For the blue box, the free body diagram looks even simpler. There's gravity and normal, but they cancel each other out. There's acceleration, which points to the right. Now, this force, of course, is the force which speeds it up. And I know I don't have much time, but still I want to ask you another question. This force acting on the left side, on the left face of this blue box, Answer number one is equal to 15 newtons. No, it is not equal to 15 newtons. It's either you know or not. There isn't much to think about, so you don't have to spend a lot of time. So, wrong. Yay. You should ask yourself every time, is this object touching that object? If the answer is yes, well, that object does exert a force. If the answer is no, that object does not exert a force. So, is the hand touching the blue box? Everything just gone. Yes or no? The hand. There's my hand right here. This force, yeah, that's the hand, or I don't know, a stick or something else. Something is touching that green box to make it move. So it's a good thing to imagine the actual hand. So now, if you look at this picture, you can ask, is the hand touching the blue box, yes or no? No. So that cannot be 15 newtons. 15 newtons is the force exerted by that hand. So we got to write that's the force acting from green on blue. Relative to my x-axis, it has a positive component, and acceleration points for the blue box points to the right. So the mass of the blue box times acceleration of the blue box has to be equal to, there's only one force which is responsible for this acceleration, because again, gravity and normal just cancel each other out. Strictly speaking, that's what we're doing. This plus this plus this. That is what the net force is. But this plus this equals 0. That's what canceling out means. So what's left is this force from the green box and the blue box. And again, we have two unknowns. What does it mean? We give up. No? No, because we never do. We know that we can treat the whole system as one object made of two individual boxes. This whole system now has a whole mass, total mass, which is equal to 3 to 5 kilograms. And for this system, gravity and normal forces also cancel each other out, so they do not matter. The friction, which should have been included in a real life situation, has to be neglected because we are told so. There's only one force which is responsible for the acceleration of the whole system. And if you write the Newton's law now, we should write 15 newtons has to be equal to 5 kilograms times the acceleration of the whole system. And the acceleration of the whole system will be equal to 15 over 5, 3 meters per second squared. Well, they move together. That's what we call the coupled motion. They coupled. So if the green box travels 1 meter to the right, the blue box travels 1 meter to the right. For the green box travels takes 1 second to travel 1 meter, I don't know, yeah. That means for the blue box, it's going to take exactly the same time to travel exactly the same distance. So they make the same displacement, they travel with the same velocity, and of course, they have the same acceleration. So this acceleration, which we have calculated and we call the acceleration of the system, at the same time, the individual acceleration for each part of the system, including the green box, including the blue box. So the immediate conclusion is the acceleration of the green box is equal to the acceleration of the blue box, which is equal to the acceleration of the system as a whole, equals 3 meters per second squared. Now, if we look at what is happening to the blue box, there is force acting on it. We called it from green on blue, and to other forces which cancel each other and not responsible for the acceleration. So now this force has to be equal to the mass of the blue box times the acceleration of the blue box, which is 2 times 3, 6 newtons. We can go back to the green box. For the green box, we know 2 forces acting on it. 15 newtons from the hand, and there is some amount of force acting from the blue on the green. Now, can you tell me that amount of force acting from a blue on the green? Because someone said 6, that is a correct answer, but there is a reason for everything in physics. What is the reason? Yes? And what is the name for this statement? Exactly. So the reason in physics is either a definition or now a law. There are only 2 reasons. It's a definition or a law. That's it. For this situation, the reason for this arrow, for this force to have magnitude of 6 newtons is the Newton's third law, which tells 2 objects interacting exert forces which have opposite directions and same magnitudes. If this was the force from green on blue, the force from blue on green should be opposite to that, but same length, same magnitude. So now we can calculate the net force. F net supposed to be equal to 15 newtons to the right plus 6 newtons to the left, which gives how many? 9 newtons to the right. We could have done it differently. On the other hand, the net force must be equal to m times a, but that should be m green times a green. M green is 3, but the acceleration is the same for all of them, 3. 3 times 3, 9. So we always have extra equations we could have used. It doesn't matter. If we do it correctly, we always arrive at the same result. And sometimes, at least when you're doing homework, it's advisable to try all possible ways to arrive at the same result and see if they match. If they match, that's it. You're good. If not, you may have made a mistake. Any questions? So there are slides. This is a problem which kind of have been solved. Well, at least we started to do it. Again, we have a system of two objects connected. And I just repeat first what we did. There's a tension force acting to the right, and force of gravity and normal forces cancel each other out. So the acceleration of the box on the top times the mass of the box at the top should be equal to the magnitude of this force. Now we actually know how heavy that box is. So it's 3 kilograms times acceleration equals tension. This is the mathematical equation. Unfortunately, it has two unknowns. So we got to keep going. And we have a second object. And the block on the top is 3 times heavier, which means that weight hanging down on the string is 3 times less mass. So 3 divided by 3, 1 kilogram. That's the first equation. Now, what I did in my mind previously when I've been solving this problem, I drawn my positive vertical axis down. Let's call it W. Why not? W, it's like V plus V, which is me. Now, M times G gives 1 times 10 newtons. Of course, if we release the system, let it go from rest, both objects will be speeding up. The top object sliding to the right, the next one moving down. So the acceleration should point down. Velocity is down and speeding up, right? So relative to my choice of the positive W direction, M times A should be equal to, well, force of gravity has a positive component relative to the W axis, but force of tension has a negative component. So we can write it like that. Mathematically, it's exactly the same thing. We are adding a negative number, right? So 10 minus the magnitude of this force. This is what you have to keep in mind. Every time when you write a variable, any variable, A, T, M, G, you have to say, either out loud or to yourself, what does it mean? There's a list of meanings. It could have been a letter which represents a vector, an arrow. It can be a letter which represents the magnitude of that arrow, and it can be a letter which represents the component of that vector relative to a certain axis. 3 different meanings. And you have to stick to that meaning until you have the problem solved completely. So this letter T represents the magnitude of force of tension in the string. So that's a system. 2 equations, 2 unknowns. So for example, we can solve the first equation for the tension force. Well, it's solved already. Just plug it in here. 1 times A is supposed to be equal to 10 minus 3 times A. Bring it over here. 4A equals 10. A equals 10 over 4, 2.5 meters per second squared. 3 times A equals 3 times 2.5 equals 7.5. That's got to be equal to the magnitude of the tension. So This is a simple problem, but it's a perfect illustration of the strategy which we have to use every time when we have to solve a problem. When two objects move together, coupled motion. They coupled by the string now. Well, so this is what we already have talked about. This is what we should talk about as soon as possible. Let's briefly mention, so again, gravity or weight. It always points down, and that's how we calculated magnitude when we're close to the surface of the Earth. Otherwise, the expression would have been different, but that's a different topic. If we're close, within like several hundred meters, it's definitely m times g. Elastic force. Again, what's good about it? We can use elastic force to actually measure forces because of this relationship. Again, that's what happens if you prepare PowerPoint on Mac and use Windows. That's delta. So what people sometimes get confused about, this x has nothing to do to the actual length of this spring. When we don't act on the spring, there is no force applied to it. There is no elastic force inside the spring. We have to apply a force to it to stretch it or to contract it. So this delta x means the elongation or the contraction, the change in the length of this spring. So, and in that case, the magnitude of this force is directly proportional. The coefficient depends on, well, properties of this material. It could be made of steel or copper. It could have a large diameter or small. So for any spring, we can use this fact to develop a device to measure forces. 500 grams, 0.5 kilograms times 10.5 newtons. So I can measure the stretch, and I can calculate the spring constant. And after that, I can, well, it's been calibrated. I can use the same spring to measure all other forces. The stretch is directly proportional to the force I apply. And people use this fact to develop scales. That's it. That's what it is. 0, if I apply a force, there is a spring in it which stretches, and the stretch is proportional to the force. That's it. The next important force, friction. Well, a box, it's at rest, which means it's in equilibrium. And if it's in equilibrium, net force equals 0. In this situation, only two forces acting in it, gravity and normal, and they cancel each other out. Now, I am applying an additional force. See, that's not 0 anymore. It's actually 4 newtons. Is it moving? It's still in equilibrium. That means the net force still must be equal to 0. Well, gravity and normal still cancel each other out. But what does cancel this force, which I'm applying to it? Friction. That's the only reason. If we use some oily surface, if we get rid of the friction, like this, for example, even the smallest force accelerates this already. So friction is the reason for this not moving. But you see, I'm changing the force and it's still not moving. What does it mean? That means friction immediately being adjusted to this magnitude. So if this magnitude is 4, friction has magnitude equal to 4. If this magnitude is 6, friction has the magnitude equal to 6. So this force of friction has a name, static, because it's not moving. And if I keep pulling stronger and stronger and stronger, eventually we reach critical value and it starts moving. So frictional force, force of static friction, can be any between 0 and maximum. And the maximum value is related to the normal force and conditions between the surfaces. But what's happening if I just keep pulling on it? Well, in that situation, of course, there is also friction acting on it backwards against the force which applied, but that's not the force of static friction anymore. It's moving. So how do we call it? Kinetic. And we can run many simple experiments to prove that for the force of static friction, the maximum value it can provide is directly proportional to the normal force. This coefficient of static friction depends on the properties of the materials. It's been measured, tabulated, glass on wood, steel on glass. We can find it out. Normally, it's a given number. And I'm not going to ask this question. Just think about it. What would be the unit of this? This is a Greek letter, mu, and it has no unit. That's a rare exception, a physical quantity with no unit. Newtons on the left, newtons on the right, newtons and newtons getting canceled. That's it. For the kinetic friction, when the object is sliding, the expression is exactly the same. This is the force of kinetic friction acting on an object from the surface. That's the normal force acting from the surface on this object. But this coefficient usually is smaller than the coefficient of static friction for the same pair of surfaces, normally. Not every time, but usually. And this is what I want to point at. Now, we all know everything. So what do? Well, just practice. There are two different words people sometimes use to describe the same phenomenon: resistance and friction. Friction is a very specific force between two objects when one object slides against another. Resistance is more general word. For example, here, when a golf ball flying, the force of air resistance. We don't call it usually friction. Just terminology. Tension. We're not going to learn any new equations. So we make two assumptions about any string, not a spring, a string, involved in any problem. The assumption number one, it doesn't stretch, which means if this end of the spring travels 5 centimeters, this end of the string, rope, cable, also travels 5 centimeters. So it doesn't matter how curvy it is, both ends always travel same distance over same time, so they have the same velocity. More correctly say, they have the same speed. They might have different velocities, but they have the same speed, and the magnitude of the acceleration at both ends is the same. We used this fact several slides before when we solved the problem about two boxes. But another important fact is this. Well, normally every real life string is much lighter than any objects involved. So we can always assume that it has no mass. What does it tell us? If we take any small part of this string and we apply the Newton's law to it, massless, no gravity, so there is a tension to the right and there is a tension to the left, and if we add them up all together, we should get 0 times A. 0 because it's massless. Just a second. So what does it tell us? These two forces must have exactly the same magnitude, which means inside tension, inside this string, tension always has the same magnitude no matter what. So strings transfer force from one point to another without changing its magnitude. Thank you.
We have a question. This triangle. When you make it right angles. This.
I'm listening.
Okay. How do you know what this length is? Because when you split it up, that's not 600 anymore.
But the sum of those individual parts will be equal to 600.
Yes. How do you use like the sine law, for instance? For this was on a 75 and 10.
It's either or. If this is your triangle, if you don't have a perpendicular inside, you can use the sine law.
Still can't? You can't.
You can.
You can, okay.
You can. And you should if you don't use the right angles anyway. Sine law works for any triangles. But if you don't like using sine law because for any reason, in that case you can draw a perpendicular and work it out as two right angle triangles. It's either or.
Okay. How would you? No, I can do it. Thank you.
That's a question for office hour. I'm glad, if we sit down and spend, but that's also a nice mathematical exercise to do at home.
Okay, thank you.
Yes. Yes. So,
would I be able to make it up today, or are all labs canceled?
all labs canceled.
So I wouldn't be able to make it up today.
No.
Okay.
Why?
Because I want to make it up.
Why?
Because I missed it last Monday. My lab was on Monday night.
Well, there are different reasons. If you just want to, if you worry about your grade,
Yeah,
it's not going to affect your grade. No, it's a pure math. It's not going to affect your grade. But if you just want to have more experience, probably I could have arranged it specifically, just for you to, somewhere to play around with those. So you have to know the reason. Missing the lab not going to affect your grade yet, if you're not going to miss any labs in the future.
Okay. I will not miss any labs in the future. But will you offer a makeup lab at the end of the semester?
Yes.
Okay.
In the end of the semester, usually during the last week of the semester, there is always usually different room somewhere in the basement, which has one setup of every lab. That's it. So you just have to send me an email, like a couple of two. No, not now. I will definitely forget it by that time.
Oh yeah, no problem. I'll just
So
send
you
it
will
to you
have
like
to send
2 weeks before.
around about 2 weeks before the end of the semester. You should send me an email saying what you just said. I really want to make it up. Make it up.
Okay.
And in that case, I will have to read it.
All right. Thank you.
You're welcome. Please take this. Yes.
I have lab on Tuesdays, and so I was just a little confused by the email as to what that meant for lab next week. Since Monday.
If your regular lab time is on Tuesday, that means you don't have a lab next week. What's it?
I have this.
Okay.
And so then 2 weeks
I
from
had a
now.
question too.
Okay. Okay, thank you. So next week is a special week. Monday is a holiday. Tuesday is on Monday schedule, so we meet on Tuesday, do our regular lecture. Everybody who has a lab on Monday will be doing it on Tuesday.
Okay.
And then everybody who has a lab on Wednesday For Thursday, we'll be doing on Wednesday and Thursday. So,
Okay, so it's just the Tuesday lab is pushed back a week?
yes, Tuesday lab is pushed 1 week ahead. Yeah. That's it.
Okay.
That's it.
Thank you.
Yes.
And so I missed the first discussion due to scheduling issues, and they told me I could just make up the sheet, and I had to ask you about how that factors into the grading.
Again, if you're worried about your grade and if you missed only one discussion, that's not going to affect the grade. If you want to work it through and discuss the problem, we can do it during office hours anytime with me or with any teaching fellow.
Okay.
So the different questions.
That's good. Thank you.
I have another issue. I just transferred in, so this is my first day of school starting here, and I was trying to sign up for WebAssign. I've used WebAssign before for chemistry, and it's giving me a hard time signing up, and I know that WebAssign in your syllabus is due on Wednesdays. Can I get an extension?
Well, first of all, it's not due on Wednesdays.
Oh.
That's a different. But you cannot yet log into WebAssign because if you weren't on the roster.
No, I am on the roster. I am on the roster. I just wasn't able to transfer in and start classes until my bill was paid to BU. And I got paid, so.
That's strange. That's good. For how long you are on the roster?
I've been since the beginning of class. My issue was that my bill with BU, I was waiting for financial aid to go through.
WebAssign shouldn't be affected by this, and it's really, really strange. Have you sent me an email?
No, because I was trying to fix it today on my own, but I think I'm going to call web support and see if they can get me in. But I will keep you updated with that. But I just want to know, because I think I read in your syllabus that stuff was due Wednesday, so I was assuming maybe it was due this Wednesday, and I knew I wouldn't be able to get it done by then.
No, it's not due till Wednesday. It's due.
Okay.
What you have to do? Send me right now, so I can look at my side what might be wrong.
Okay.
And 6 out of 10, I can fix it. If I will not be able to fix it in that case, I will contact the website.
Oh, awesome. Okay, I'll do that then. Thank you.
Back and forth.
Yeah.
Okay.
But do you really need it for dropping?
I don't need to take it. I just
No, I mean to drop the course. I think you don't.
Oh, I don't need this?
No, I think this is just if you're switching from one section into another, so kind of use. But okay, you can just